Okay, it's my pleasure to introduce Holger Bast from the Max Planck Institute für Informatik from Saarbrücken. He will talk about something that's similar to Google Suggest, to the autocompletion of search terms. And this talk will be posted on Google Video in public, so please don't speak about confidential information. Okay, thanks.
So this is a variant of a talk I gave at SIG-IR, the big IR conference, which just took place in Seattle. Maybe some of you have been there. In case you don't know where Seattle is, here's a sign. So it's just in the opposite direction of Paradise. So do you have an idea where this sign? So this is at Mount Rainier. So there's this spot, Paradise, the visitor center where you go. And so on the way there's this nice sign. So I really liked it. Okay, so it's about a search engine. Surprise, surprise. So let me start. Here it is. And so, yeah, I'm going to present you now a whole set of features. And I will just do this one by one. And I will start with the simple ones. So this is now searching in a small collection of computer science papers. We will later see figures for bigger collections. This is just for the sake of example. It's a nice collection because it's papers, so one understands the contents, and there's metadata. So there's information about the authors, the title, and so on. You will see in a second why that's important. So let's start with something simple. Okay, you see I'm typing something and things happen while I'm typing, so there's no search button. Now that's the first type of very simple query. So what do we see here? Here's the standard list of search results, and it's just doing prefix search here, right? So that's just document containing a word starting with Goog. So it's like as if I would have put a star here. So there's always an implicit star behind the words. And what I have here is also pretty straightforward. It's just words in my collection that start with G-O-O-G. And they are somehow ranked by importance, number of documents they occur in, and so on. Okay. Now let's do something slightly more sophisticated. Now if I type in something more, now what do I get? Now I get words starting with MOU. And actually if I activate this, I will also get phrases. So these are words starting with MOU. Again, this is still doing a prefix search on GOOG. So here I get Mountain View, for example, which means if I would type Mountain View now, I would get 10 hits for this query, right? So I could click that, and I would get, you would see I get 10 hits here, right? So the point is this is context sensitive, right? So if I would type MOU in the beginning, I would get other hits, right? So these are only completions of this word, which together with this part of the query would lead to a hit. Okay, let me just do it. Let me just type MOU here, right? Now I get other words. In particular, I don't get Mountain View, right? Because that's not a very common phrase, except in documents where there also is Google. Okay, so yeah, these are some basic features. And there are more to come. Okay. Okay, so first so that's already somehow useful, right? So I call this basic autocompletion. Okay, it saves you typing. You only type as much as you need, right? Maybe you think you have to type a very complex query, but actually you find that after just one word or even a few letters, your thing is already there. Then what's interesting, by this thing on the left, you find out what's actually in the collection, right? So there were, I don't know if you saw them, there were words like Googlism, Googlearchy, which you maybe didn't know before, and so it's just interesting to see them, right? And there's also some amount of error correction, at least for errors occurring towards the end of the word. And we can also do something about errors in the front. Okay, but that's just... Now you can do more sophisticated things with this feature, which is not so obvious. So one thing, you can just complete to phrases too. How do you do that? If you identify a phrase Mountain View in your collection, you just add this word to the collection, right? So then you also have phrases. You can also complete to subwords. Wherever in your collection you have the word eigenproblem, you just also put the word problem into your index. So let me just show this, for example, here, right? So here I have algebra. Now I type problem. Yeah. So for example, now it also finds algebraic eigenproblem, right? Because it just found, oh, this is composed of two words, and so I also put the word problem here. And so it finds it, although these words start with eigen. Okay. Still pretty straightforward. Now, a little bit less straightforward. I have metadata here. Metadata is very useful. These are papers. Paper has an author. It has a conference. It appeared in a certain year. For example, there's this author. It's also starting with MOU, right? So that's one information retrieval guy. When I have this author, I just add this artificial word to my index. And also this artificial word to my index. What do I gain from this? Now I can also complete to this word. So I just activate this here. Yeah, so now if I do again, okay, now I'm again, I mean, this has 628 hits, right? And now I type MOU. Okay. And so now it also completes to this metadata thing, right? So here's something which starts with MOU, and so it asks me, maybe do you mean this? Do you mean this guy Edleno Maura, the author? And this would lead to 2 hits together with the word Google. So that's also quite useful. Yeah, and if I would type something Edleno, I would also get something. Now, even less straightforward, I can do something that's known as faceted search. All this metadata, when a paper is from SIG-IR conference, I just add this word to the index. I just add this word to the document as if it were there. If a paper is by Edleno Maura, I just add the word CT:author and so on. If it appeared in this year, I just add, what do I gain from this? Let me show you by an example. Yeah, again, let's stick to the Google thing. So here are my 628 documents. What do I get now if I type this CT: thing? Now we get all words starting with CT:, that together with this GOOG would lead to a hit, right? And here these are just the artificial words which you saw on my, yeah, I just rewrite them there when I show them, right? I don't write CT year, I just write the year 2005. Okay? So this is just the same thing as before, but just a little bit of rewriting done. Now that's of course not so, I mean, which user will type CT:? You don't want to do that, right? You don't want to ask your users to do that. But you can always launch this query automatically in the background, right? Whenever you type something, you also launch the query with CT: appended, which is just, yeah, which is when I have the full thing. Yeah, let me make the font a little bit smaller for a second. And the boxes, okay, yeah. So this is actually the full set which you would get. So I type something. I will make it larger again. So here are my completions. And now these are the completions if I would append the CT: thing in the end. So in this 622 hits, 2 are by the author Kerry Roden. 162 appeared at www, 85 at SIG-IR, and so on. 221 in the year 2005. So this is what's called faceted search. You maybe know this from sites like eBay or things like this. Is this clear? Is there any question? Perfectly clear, good. Okay, so these are all nice features, and the point I want to make here is, I mean, you get all this via the same mechanism, right? It's just this prefix completion thing. Just by doing different things with your index, invoking the same mechanism, you get a whole variety of useful features. Okay, 2 related things. You might have seen that before. Okay, so people who see this, sometimes they say, oh, this is just Google Suggest, so let me just point out the differences. Let me say in advance that I like both of them, but they are just very different, and I think it's important to understand. Yeah, so let me just type. So what's the difference? Oh, actually, it's my home page. Yeah, for example, okay, I also get these things. Okay, first thing, I mean, it doesn't search at the same time, right? You just get these completions. But then, for example, if I type in the name of my host, Hein, I don't get any completion. So why is that? I mean, this is not doing some full text thing. This is just completing to queries which people ask, right? Which is a very natural thing for Google to do because you guys have all these query logs, right? And so that's just a totally different type of thing. In particular, it's also not a prefix search, right? If I do this, it wouldn't search for words starting with Goog, but just for the word Goog. So this is just completing to queries that people ask. So that's a different thing. And then I type return, I commit to one query, it will search for that query. So it's just a different thing. Both are nice, but it's different. Here's another thing. Have you seen this before? It's also very nice, but it's again, it's related to Google Suggest. So let me just... Oh, yeah. Yahoo. Wow, I've never seen that before. What does it say? Okay. Yeah, maybe we come back to it in a minute. So it's similar, right? In live search, you type in something, and then it also displays you a list of queries. It's basically like Google Suggest, but in the background, it already starts searching for one of the query. It snaps to somehow the nearest query, the nearest popular query, and it starts searching for that. And they have a nice user interface. Okay. Oh, yeah. Maybe I should not. Oh, but it snaps to this immediately. Yeah, okay. Never mind. Search smarter. Find faster. Okay, if it works. Okay. Yeah, just one slide for those of you who like it abstract. Problem definition. If you don't understand it, doesn't matter, right? There will be examples. So this is just this general completion thing. You have a set of documents, which is just the hits for what you have already typed, for example, Goog. Then you have a range of words, which is just the last thing you have typed and all its completions. So like this Mao. So what are potential completions? And now you just want those completions, which would actually lead to a hit, and only those documents which actually contain one of these words. Okay. And then in this SIG-IR paper, when you do this in practice, you have to do ranking, right? I mean, you get thousands of hits. You have to show the best 3. You get thousands of completions. You have to show the best. So ranking is important, but it's actually straightforward. And positional information is also important. Phrase queries, proximity queries, very important in practice, so it's easy to add. But in my talk, I will just talk about the basic thing. Okay, so, yeah, how could we do that, right? Now we want to have that feature. How could we have it? Yeah, well, let's see, how would we get it by an inverted index, right? That's what all the search engines have, at least all the big ones. You have an inverted index, one list for each word. Yeah, how would we do that? So let's take that query again. We have this prefix query, just one word. So this D from the previous definition is just the set of all documents. I'm still searching in all documents. These are the potential completions. Now I just go over all words in my index that start with Goog. This word, yeah, this is just inverted, just a snippet from an inverted index. And now I'm doing a prefix search, so I have to merge all of them. I want to show any document containing a word starting with this. Okay, I can do that, but that's expensive. That's a problem, right? That's why big search engines usually don't do prefix search. It's expensive. You can do it, but it's expensive. Okay, and there's nothing context sensitive for the first word, right? Every word that's in the index will also lead to a hit. That's why it's in the index. So I just output all these words in my left column. Yeah, so this is easy for one-word queries. Let's look at the same thing for a two-word query and same thing for 3- and 4-word queries. Yeah, this one we tried. So here I put the stars, right? In the engine, you don't have to type them. So now my D is, this is the set of documents. This is the hits for this part of the query, right? And as I'm typing more, I'm zooming in more. Now these are all words matching this, all words starting with Mao. But some of them will not occur in any of these documents. So now what do? Again, I go over all the words. There's mold. And I find no mold in this set of documents, which means mold will not lead to a hit together with goop. Intersection is empty. Mount, in my example, also doesn't lead to a hit. Mountain, there's 3 and 18 leads to a hit. So mountain should be displayed in the left column, right? Mounting, again, intersection is empty. No hit. Maura, this guy, the family name of this author, again. Okay, so what do? I just go through all of them. I intersect. And when the intersection, I merge the non-empty intersections, 3, 18, 25. And I output the words where the intersection was non-empty. Okay. So the problem here is, most of these intersections will be empty. And there will be hundreds of words here, right? Index, you have all these strange words. You will have to go through all of them and compute the intersection for each of them, just to find out that it's empty, and just for a few of them. And that's really a problem. So just a summary of the problem. So it's 10 more minutes. So what does this mean? When you write down the complexity, it's bad. And I've given you 2 reasons. Many intersections. You have to do many intersections. And you have to do some kind of sorting because it's a prefix search. You have individual lists. You have to merge them. And merging is expensive. But when you work on this, and we are working on this for 2 years now, when we started, we did a lot of things, fancy things, nice theoretical bounds. It was very hard to beat this simple thing in practice. Why? Because the inverted index has a lot of very nice properties. Let me just summarize them. Inverted index is highly compressible, right? You can compress these things very well, which is important because, you're fetching these things from disk. I don't know if you are doing this, but still, if you are fetching them from memory, it's the same thing. So half the space on disk means half the time to read it. Half the space in memory means half the time to read it. Inverted index, if you do it right, has a very good locality of access. You just read your data from contiguous blocks of memory, right? Which is very important because, as you know, there's this ratio. Doing 100 accesses in memory here, there, or doing them contiguously, that's a factor of 100, right? So very important in practice. Yeah, and it's just simple code, which also plays a role, also for efficiency. Okay, so here are 2 slides on what I suggest, what we suggest. The basic idea is, you're doing prefix search. Just have lists for whole ranges of words. That's the basic idea. We will see that it's not so easy to make it work. So this is just, somehow I just pre-computed this union, right? Yeah, but now, now if I find out, okay, document 16 is a hit, I don't know because of which word in this range it was a hit. That's bad. So what do? Yeah, I could just write the words. So document 16 came into this range because this word was there. Document 18 came into this range because of these 3 words. So I could do that, but that doesn't look like it would work, right? I have these lists, and then I write all these words there, and they are different length. So that's why we didn't come up with this in the first place, because it doesn't look like it would work. Okay, here's one slide how you can make it work. Just some basic ideas. you have these blocks, which you have seen on the previous slide. Now a little bit more abstract. These are document IDs, right? So this is one block, and now this list of document IDs, 1, 3, 3, 5. And here I just have the words. And if a document has more than one word from that range, I just repeat it, right? So document 3 has word A and word C from that range. Here it's the range A to C. These are just some artificial words. Now, here's something. This is a very long list, and it has small gaps between the numbers. So let's just replace the doc IDs by gaps. And also here, some terms are much more frequent than other terms. So let's just replace each term by its rank. So this is just the gap. 1 from the beginning, it's +1. To the next one, it's +2, +0, +2. Yeah, it's just the gaps. And this just means D is the third most frequent word here. A is the most frequent word here, so I put a 1 here. What do I gain from this? Now, I have a lot of small numbers here, right? I have a lot of small numbers, and now there's some encoding called universal encoding, where I encode a small number with few bits, a large number with many bits. And actually what you can do in theory, you can encode number x with log 2x bits. It's not obvious how one can do that, right? When you want to encode numbers of any size with this property. So here's, huh? Yeah, that's the theoretical optimum, and you can get somehow arbitrarily close to it. But then there's a trade-off of how hard is it to decompress, but you can get very close to that. Oh, yeah, so here's just some encoding scheme, right? The +0, I will just encode with a 0, plain 0. The +1 with the 1, 0. The +2 with the 1, 1, 0. And this must be prefix-free code, right? So that when I go from the left, when I see a 0, I immediately see, oh, this is a +0, right? And so on. And I also encode these ranks. So what the numbers are, it's not important. Yeah, and now this monster here has just become this very compact sequence of bits. Yeah, now the question is, I mean, is this good? Now I just did some random things, I gap, ranks, some compression. I mean, could do so many things. Actually, we did it the other way around. We ask ourselves, there's something called entropy. You can ask yourself, I mean, how well is this compressible in theory? And then you can write down the empirical entropy of an inverted index. You don't have to understand this number. It's just interesting in comparison to the next number. Oh yeah, and there's also an issue. There are these blocks. How do I choose these blocks? Of which size? I mean, how should I divide my things into blocks? It's not clear, right? I could experiment, but I mean, there are so many choices. And so here's a... So ni, that's just for the ith word in how many documents does it occur, and n is the number of documents. And here it says if I choose my blocks of this size, it's not important what it is, it's just some size with some parameter epsilon, I get this entropy, which is essentially, I mean, this is the part that is big, and this is the part that's small. So I get a very small epsilon here. So this somehow, in theory, one can show that this, what I showed you on the previous slide, should work well. Okay, now we just tested it on some collections. They are not as big as what you have, but at least it's this biggest IR benchmark included, this .gov collection with half a terabyte of raw data. I mean, it's harder to have bigger collections because you have to get them on your computer. Yeah, and the nice thing here is, I mean, when you actually do this, you implement this, then, I mean, you actually see this, right? You can do this and just a little bit more, you actually see this epsilon. So, I mean, theory and practice match almost perfectly here. So this entropy thing predicts exactly, when you use a good compression scheme, what you can achieve. Which means you can do this at no loss in space. Okay, now we have to look at, is it also fast? We wanted to do it fast, so I will just do this very fast. Yeah, there's some analysis which you can look up in the paper if you're interested. Yeah, we just did some, yeah, this thing now avoids merging and yeah, all this stuff which I pointed out for the inverted index. So what would we do? You just take some ordinary queries and you just type them from left to right, right? You just pick some and then you just measure the running time. So for example, you take the query Google Mountain View and now you just type it from left to right and you just measure how much time does it take after each keystroke. Yeah, okay, and here's the, yeah, okay, yeah, you just see this improvement by a factor of 10 or something like this. So it's very, yeah, it's an order of magnitude. And what's actually important is the maximum here, right? I also have the average here, but the maximum is more important. Somehow, you don't want it to take long sometimes, right? You always want it to be fast. If sometimes you wait for a second or two, that's not so nice, and you have this effect here. Sometimes waiting for 16 seconds is not what you want. So here we remain in the sub-second range, even for this terabyte thing, or on an ordinary single machine, right? Which is quite remarkable, I think. Yeah, please.
You were about to say something, I think, about choosing the blocks depending on the entropy measure. How did you decide to choose what the ranges were?
Okay, the question was, I said I would say something about the block size. So it was on the slide, but maybe it's here. So the theorem says if you choose the blocks of this size, where the size of a block is just, yeah, this block has size 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 16. It's just the number of items here, the number of columns of this thing. So this is a block of size 16. And now the theorem tells me, which is something you would have not guessed in advance. If you take the blocks of size epsilon times n, where n is the number of documents, so 25 million for this terabyte thing, then this is the number of bits which your index uses. So you get this epsilon here, which means you should choose the block a fraction of this 25 million. So for this terabyte thing, you should choose blocks of size a million, a few millions. And you couldn't have, yeah, you wouldn't have guessed that. And the theorem tells it to you. Yeah, and this is, I mean, these numbers are for this block size. Oh, and what I haven't shown you, when you do the analysis here, for the queries to be fast, the blocks have to be large enough. And so it just fits together. So they have to be of size epsilon times n, and then it will be fast. Okay. Oh yeah, just very briefly, maybe interesting. So how, I mean, this is a system running via the web. I mean, what did we do? Okay, so there's this server thing, right, which is just answering the queries. You type something, Google Mau, and now it should give you the completions and the hits. So that's, of course, written in C++ and C, otherwise it would never be so fast. Then in the middle, you just have a web server doing PHP. And on the client side, you have a lot of JavaScript. Yeah, and just very high level. I mean, you type something, this sends a request to the web server, this sends a request to this server. It's important to have this middle thing so that you don't get any problems with firewalls or JavaScript. I mean, the client can't talk directly to some server, or you shouldn't do that. And then this goes back here and goes back here. And this is what happens after every keystroke. Yeah, and whoever has done something like this, it's only 3 components, but debugging something like this, it's terrible, right? If you have an error there, it's a network application, so which means you always have these effects which are not reproducible. And I mean, you have these things, JavaScript, PHP, they are not, I mean, C++ is hardly standardized, right? But for PHP and JavaScript, you have these subtle differences between browsers, and it's a network application, so that's really a lot of work. Okay, I summarize. yeah, these were the properties. So there's this blockwise index. You can compress it as well as the inverted index, which is very important. You can do these completion queries, which I showed you, and all these advanced kind of queries very fast, because you have perfect locality of X. You're just scanning data. You never do anything else except scanning, and that's very fast. Indexing is much faster. I didn't talk about this, because this block thing, you don't have to fully invert your data. You just need a half inversion, which also means when indexing, you don't have to sort, which is very significant. Okay, and then you can do all these things which I showed you. You can do this faceted. Yeah, that was a workshop talk on SIG-IR. I didn't talk about this. Yeah, this is new. I just give you an example. You can also use this to ask this kind of queries, which you can't. This means, give me all authors which have written a SIG-IR paper as well as a SIGMOD paper. So these are two different. SIGMOD is the big database conference. SIG-IR is the big IR conference. You can't write a keyword query out of this. If you write a keyword query, SIG-IR paper and SIGMOD paper, this will be the empty set. No paper is SIG-IR and SIGMOD paper at the same time. If you do an OR, you will get authors which have written either. But if you want authors which have both, if you have seen XPath, XQuery, that's related to this. So you can do that too with this index. Okay, and the bottom line is, I mean, you have this set of features and you don't implement them ad hoc, but you have one mechanism which you implement efficiently and you get all this. Okay, so that was my talk. Would be happy to answer some questions. Yeah, please.
So I have several questions. One question is
Good.
how about the scalability of your algorithm? In other words, how do you choose the block size and how does that affect the scalability?
How do I choose which size?
Block size.
The block size. Okay, the question was how about scalability and how... Okay, I haven't shown you this... I mean, it's... Yeah. I mean, how the block size is to be chosen, this theorem tells you. You just have to choose it dependent on the number of documents. Yeah, of course, it goes up. I mean, it goes up linearly with the collection size. So you can't do anything about this. The only thing you can do about this is parallelization. So the query time is just linear in the number of documents in the collection, which you can sort of, yeah, see here, kind of. And so, yeah, if you want some, yeah, if you have much larger collections, you have to use several computers, of course. But the point is, I mean, yeah, it's always, you don't have this merging stuff and like in the inverted index. It's just an order of magnitude faster. So you need an order of magnitude less resources.
Number of words there is number of distinct words?
Or? Oh, no. Yes. Okay, which one was right? This is the number of distinct words, yes. It's not the number of tokens. Yeah, I mean, number of distinct words is always larger than the number of documents, right? Because you have so many strange words. So this has really 25 million different words. But they are very strange words. You just don't throw them out. You had more questions?
Yeah, another question is how about updates? If I I add some new documents, then all these blocks needs to be regenerated.
Yes. Okay, the question was how about dynamic updating? That's the same as for the inverted index, and I mean there are standard techniques for doing it, and that's also how we do it here. That's not so bad actually. You just have a smaller index, right, in which you rebuild all the time, and if it reaches a certain size, you merge it with a bigger one in the background. And actually, you have a hierarchy of indices. So that's a standard trick which you use for inverted indices, which you can also use here. Another standard trick is you have your index and you just leave space in the index so that whenever you have new things, you don't have to, it's an array, right? And if you don't leave space and you have to insert one thing, you have to copy everything. But if you leave space, just put it there. So these are two standard tricks which work for both kind of indices.
A related question is a dynamic update. Suppose you find a million pages which are spam. How do you delete them from your index?
Deleting?
Yeah.
That's also a standard thing. Deletion you can do just like insertion. You insert the document with the tag deleted. So that's the way. I mean, I want to delete a document, so what do? I insert it as a new document, and there's a tag deleted. And when I find this one, it says, here's a hit, but it's actually deleted. I will also find the old one. There will be a timestamp. This is newer. And then after some, in this background merging, at some point, they will actually be purged, right, and thrown out. So that's how we do it here. So that's just the standard way. It works. But
So if the number of documents have changed largely, would you reselect the block size and regenerate the whole block?
oh yeah, I should repeat. Okay, good question. So if the collection size changes a lot, then also the block size should change, right? So we haven't worked on this dynamic aspect so far. We just made it work somehow, but that's an interesting question. You would have to do it somehow, that's true. But you would probably also do it in this rebuilding in the background, because it will take some time until it grows bigger. But it's an interesting question, yeah. Yes?
I have two questions. The first is, can you be more specific about what epsilon is? I understand how it's used, but how do you choose it? What's a reasonable number for what epsilon is?
Yeah. Oh, the question was, there was this epsilon parameter, so what's a reasonable value? Actually, there's not much magic about this. It's just you choose it 1 over 10, or 1 over 5, or 1 over 20. I mean, if you choose it right, it will just blow up the index insignificantly, and it will not... Yeah, I haven't told you the details of the theoretical analysis, but it just doesn't matter much. So it's not a tuning parameter which plays a big role. 1/10, 1/20, something like this. Okay, you had two questions?
A little more generally, I'm not entirely clear on what the block size is. Is it the number of terms that you lump together into a single...
Yes, okay. The question was, what exactly is the block size? So if this is a block, then the block size is 16. It's the number of columns here, the number of pairs. Here I have 16 pairs. So that would be block size. It's not, it could be the number of different words, right? But that's not what it is. It's the number of items here, the number of pairs.
How do you decide how to collect your words together into a range? How many words do you put into a single range?
Oh, I just do it via the block size. I say the block size is 1 million, and then I just cut it. And it actually doesn't matter if it cuts right. So if the word is here and there, and it just doesn't matter. It's not important. I mean, I didn't tell you details about this, but it's implemented. And so there we didn't, yeah, it doesn't matter.
So is it important to have the full vocabulary before you start implementing those blocks?
Can you say it again?
The full vocabulary. Like if I add new documents with new vocabulary, how does it change the blocks? Like if there is a new word that drops inside the given block.
Yeah. The question is when the vocabulary also grows, right? When you add new documents, you might encounter a word which has not been there before. How do you do it? So we haven't paid too much attention to this dynamic updating thing so far. But again, you can do it with standard techniques. I mean, you just give it a new word ID. I don't see the principal problem in doing this.
So there is a word
Yeah.
range. and it contains words from this MO, L to MO something.
Yeah.
And there is another word that drops inside of it. So do I have to discard the whole block in order to rebuild it?
Okay, what you would do is, again, you would just leave space, right? You would just leave some word IDs in. In the index, these are all IDs, right? It's not words. You don't write the words there. You just write IDs. And so you just leave some IDs in reserve. And actually, you don't have to map such that the alphabetical order gives the word IDs in increasing order. You can have a slightly different mapping there. And so like this, you can play tricks. You just leave some word IDs, and then you... But eventually, when it grows too large, you will have to rebuild, right? That's always the same thing. But we haven't worked out all the
vocabulary of size n, then you can just leave a lot of spaces in.
Yeah, just half, just leave the same space again. I mean, that's 1 bit, right, which you waste. It's no problem. Yeah, it's always this, when you rebuild, it's always this factor 2 thing, right? When it grows twice as large, then you rebuild. And then, yeah, overall, it's still linear. Yeah, more questions.
Yeah. I mean, this is an application. Suppose I'm typing a paragraph. Why do you always choose the contiguous words? There might be some important words in the paragraph I want to complete. Say to be or not to be, and then Hamlet somewhere in the paragraph. So you want to pick a document that's related to the sentence I'm typing. And you always seem to pick the last 2 words or whatever. So I want to complete based on everything I've typed, like in Emacs does, like a completion which is useful on what I do, not based on what you do.
I'm not sure whether before I repeat it, I have to understand the question.
So the words that you complete on are the last 2 words that you type. Suppose you type in 10 words or 10.
Okay, you're saying, here I'm completing only Mao and not Goog anymore.
No, but you're using Goog as an important direction. So suppose there are 10 unimportant words in between. How do you pick which words to pick?
No, all of them are picked. Okay, it's still hard for me to repeat the question because I'm not sure. Maybe I just explain. Somehow the question is what's happening when I type in more than 2 words.
Maybe like 100 words.
Okay, but for 3 words, I mean, just to make it clear, this is a prefix query, right? It's Goog star, Mao star, and it has 133 hits. Now, if I type further, I'm searching in these 133 hits, and I'm getting completions of words in these 130. So in 89 of these 133 hits for Goog star, Mao star, there is a word view. And in 32, there's viewing. So it's taking all the words which I previously typed into account. So then,
can you ignore words which are like very common in the whole sentence? Ignore, like suppose I type to be or not to be.
Yeah.
So some words are very common.
Yeah. At the moment, they are not ignored, but I could ignore them. Do you think I should ignore them? The question was, can I ignore? And I asked, should I ignore?
To complete on. And pick some words to complete on, like important, statistically improbable phrases.
Yeah. Yeah, one could do that. The reason is that I didn't throw anything out is so because you can also have phrase queries and things like this. Yeah, but it's true. I mean, when bringing this to a larger scale, one should probably think about the and be and these words. But right now, they don't make problems.
So another question is?
Another question, yeah?
I mean, most of the people seem to be happy with like just a few, like a small dictionary. So why do you want such a big, like a 26 gigabyte dictionary for most people? Why would people be happy with a big dictionary of completion of phrases? What's the advantage of using such a big dictionary?
I mean, Google indexes every word, right? I mean, Google does the same thing. Every 5-letter word which you type has a hit. You type PFCHY, it will be a hit. because it's hard to tell whether this word is meaningful for anyone. So you better don't put it out. And anyway, I mean, you can just store it, right? It will not use so much space. But as soon, I mean, you're typing 3 words, VIE, and I mean, this will rule out, I mean, we'll just, yeah, now you're only getting, yeah, you don't see any strange words here, right? Although there are a lot of strange words here. So it just doesn't matter. Why should I bother to throw out the strange terms? I just keep them there in case somebody types YZPQ. I mean, then he will get the completion. Maybe he was looking for it. Google does the same thing. It's hard to say this term is not useful.
Now I'm saying the benefits versus the completion cost. How many people would want to search like this?
Yeah, but the thing is that all these strange terms are very rare. So they actually don't cost a lot. You can just put them in your index. Otherwise, yeah, that's a standard thing.
But then your search didn't went up linearly in the document. The cost went up linearly in the size of the documents.
In the number of documents,
yeah.
Not in the vocabulary.
That 26 gigabyte of data.
Yeah.
That took a lot of time.
Yeah, but it was the number of documents where it was linear. But you're right, but I mean, it's a factor of 2, I think. You save a factor of 2 if you throw out strange words. But that's just a factor of 2 and not 10. So if you want to save, or you just buy another machine and then you can. And as I said, so Google has also opted to, yeah, because somehow it's hard to say this word is not useful. Maybe it's useful for someone.
Yeah, but is he paying for it?
Huh?
Will he pay for it?
Yeah, Google pays for it. I don't know why. Apparently. I mean, you tried this, right? Type any 5, I mean, just to, just type any, okay, yeah, maybe this was PQVSL. Yeah, I mean, there's just type any, and I mean, 5 letter words, they're a lot, right? It's 26 times 26 times, type any 5 letter words into Google, you will have, okay, it's just 34 hits, but it adds up. So apparently, yeah, and maybe that's, yeah, I don't know, it means something, some language. Yeah, okay. Thanks for listening.